This is problem 3-37E. It's on page 153. A spring-loaded piston cylinder device is initially filled with 0.2 pound mass of an R134A liquid vapor mixture whose temperature is negative 30 degrees Fahrenheit and whose quality is 80%. The spring constant in the spring force relation F equals Kx is 37 pounds force per inch, and the piston diameter is 12 inches. The R134A undergoes a process that increases its volume by 40%. Calculate the final temperature and enthalpy of the R134A. Okay, so let's write down the problem number. Try to solve this thing. Spring-loaded piston cylinder device. Okay, let's sketch it. And let's see, does the volume increase? Yeah, the volume increases, so I'll draw the piston fairly far down. It's spring-loaded. That just means there's a spring off to the side that's pushing down on it. We're told that the spring is linear. And I'm going to say F equals Kz so that I can measure the position upward from the bottom of the z-axis. And for this particular, well, we'll talk about that in a minute. Let me make a z positive axis like this. Anyway, the spring constant K is 37 pound force per inch. Be careful, we talk about pounds of mass and pounds force a lot in this course. There's a difference. Pounds force is force, pounds mass is mass. And the 1 pound mass, of course, will weigh 1 pound force on Earth, but not on the moon. What else do we have? Well, the diameter of this thing is 12 inches. And let's see, other information, the mass in the system is 0.2 pound mass. Temperature is negative 30. So the initial temperature, now I'm going to go ahead and write a state 1 because there's a different state. We know there's a different state. How do we know? Well, the volume increases. As soon as a property changes, that's a different state. So we need to make a distinction between state 1, process occurs, and then state 2 exists, okay? So there's a difference between the two. So let me write T1. Notice I didn't write M1. Why would I not write M1 and M2?
Because the mass doesn't change.
The mass doesn't change. It's a sealed system, right? So let's not forget that this is R134A, and the mass in the system constant. Anyway, the initial temperature is negative 30 degrees Fahrenheit. And they tell us that the quality is 80%. Now, so far I've used a symbol for everything. What symbol should I use for quality? Do you remember? Y do we want, or Y?
Y, like the letter Y.
Almost.
Is it letter X?
It's an X. We use X for quality. What is quality, physically?
The amount of energy before it returns into its lower state.
The amount of energy? Is that what you said?
Yes.
Okay. No. It's okay. Good answer for now, bad answer for the exam, right? Now's the time to make those answers. What is quality? Somebody else. Or go ahead if you remember.
It's not the comparison of mass, it's liquid versus gas.
Basically, yes, just a percentage, right? It's what percentage is there in the gas phase. At 0% of the mass is in the gas phase. At 100, all of it's in the gas phase. Does that make sense? At 50, half of the mass is gas, half of the mass is liquid. So just think of it as a percentage. That's the easiest way. So the quality in state 1 is 80%. So again, what does that mean? Well, what's 80% of 0.2?
0.16.
0.16. That means 0.16 pound mass is vapor. The other 0.04 pound mass is liquid. That's all it means. There's a little bit of liquid and a whole lot of vapor. My drawing's probably pretty darn inaccurate because I don't know how much of the liquid you would actually see. You wouldn't see much of it because the volume of the gas would be so much more. But for our purposes, that's okay. By the way, what is R134A? It's a refrigerant. Where is it used? It's used in cars, that's true. If you're, there's a YouTube channel I'll show you guys. I don't want to put it on the video. It'll just waste time on the video, but I'll show you, and then I'll add a link. I'll add a YouTube video in the There's people that actually play with this stuff for fun. You might be surprised to find that. It's so interesting, some of the things they can do. Anyway, so R134A. Let's see, what else? Well, we're given a little bit more information. Basically, I'm just trying to get all this stuff on the board, right? Just trying to figure out what all do I put where. Okay, R134A undergoes a process. Well, here's the process. We don't know what the process is. It doesn't really matter. That increases its volume by 40%. So in the next state, the piston has been compressed again a bit against the spring, or another way to say that is the R134A has apparently expanded so that the volume in state 2 is 40% more than the volume in state 1. Does that make sense? So 140% of the volume in state 1 equals the volume in state 2. And what do they want to know? Calculate the final temperature and enthalpy of the R134A. So what's the final temperature? And what's the enthalpy in state 2? Now, before we jump into all the gory details of solving this, let's talk about it from probably an energy perspective, right? That's what we usually talk about in this class is energy. So in terms of energy, what all has happened here? How did the R134A increase its size? How could it do that? Apparently energy flowed into it. We don't know how much energy flowed into the system, but apparently some did, right? Where'd that energy go?
Into the gas.
Pressure on that. It pushed the weight up.
It pushed, okay, so some of it went into the spring. Good. What else?
Is there any friction?
We usually would just assume frictionless, and also that the gas doesn't expand quickly and all those things. So something we'll talk about later that's called reversible, but for now that's not important. We're just assuming it. What else? Where else did energy go? Does it take energy to get something to boil off?
Probably went into that liquid then.
So some of it went into the liquid to boil some of it off, right? In other words, there's been a deposit of energy. They didn't clearly state that. But from what's happened, we can see that that has happened. Why? Well, the bank account increased, right? You look at your bank account, you have $100 today, tomorrow you've got $1,100. It's a good thing, right? Somebody deposited $1,000. This is wonderful, right? What's bad is when you look in your bank account and somebody's withdrawn because you set off automatic bill payment or something, right? Anyway, so money was put into here, or energy was put into here. Okay? So that energy, some of it's still in here. We know that because we know that the volume has increased. The only way the volume would increase is if some of this liquid boiled off. Not only that, but yes, some energy has gone into the spring. Now, if we knew the mass of the piston and how high up it had risen in the gravity field, we could talk about the potential energy change of the piston, but we have no idea about that. We might get at how far the piston has moved, but we really don't know if this is even correct. It could be upside down. Right? So the piston could have actually gone down, not gone up. We don't know. There's one more place, though, that energy went. Remember in 220 when I told you about how difficult it is
Into the spring.
when you're under the water, not dead, but diving? And you want to blow up a balloon. Now, this is not a taxi balloon, this is a balloon. Would it be harder to do this underwater or out in the atmosphere? Underwater. Why?
Pressure.
Well, you got to lift the water out of the way. Do you realize that we live under an ocean of air? That air is pushing down on things. So what else did the energy have to do here? What's that?
Boundary work?
Boundary work. Very good. It had to push the atmosphere out of the way. Okay? That's another big thing. The amount of boundary work that it did, you could say the boundary work went into the atmosphere and the spring as a whole, because you're right, all of it's boundary work. But in an intuitive sense, it's nice to know some of the work went here and some of the work went out into the atmosphere. Okay? So the deposit that was made into this account did not all stay in here. Some of it stayed in, some of it flowed out. Now, they didn't say anything about heat transfer, so we'll have to assume no heat transfer. Now, wait a second. They asked for a temperature in state 2. If there's no heat transfer, wouldn't the temperature just be the same? Not necessarily, right? Because energy transfer is what causes a temperature change, not just heat transfer. Okay? All right. So we've kind of danced around. What do you think we ought to do here? Probably an energy balance, right? We almost always have to use an energy balance. balance. That's what we do. So let's see if we can write this down. Well, let's see.
Is this an ideal gas?
Good question. Is there any liquid in it?
Yep.
Is it an ideal gas? No. Right? It's the ideal gas law, not the ideal liquid law. Okay? Good question. Good question. So we can't use the ideal gas law from the beginning. Let's write down an energy balance, though, and see what we come up with. Now, we weren't told about any heat transfer, so I'm assuming that it's zero. So how would we write down an energy balance? Well, I say there's no heat transfer. What I'm trying to say is there's no heat loss. I would assume you probably just put heat into the system to make this happen. You could put work in. It doesn't really matter. Either one would work. Let's talk about heat flowing in, but not heat flowing out is what I'm trying to say. Okay. So heat in minus boundary work out, and for right now, I'll just let this represent the work done against the spring and the work done against the atmosphere. Okay. Well, let's see. So that's where energy flows out, energy flows in. That would just change the energy in the system, right? Basically, there was a deposit of energy here into the system. There was a withdrawal of energy here coming out, and that changed the amount of energy in the system. Make sense? All right.
Q in this would have to be greater than the boundary work energy.
I would say so. In fact, you could rearrange it and say Q in changes the account balance and provides the boundary work. Right? The rich uncle gave you some money. You spent some of it and saved some of it.
Thanks, Rich Uncle.
That's all right. Thank you. Or aunt. We don't care.
Yeah, we don't care. Don't judge.
Rich stranger. Go ahead. I'll give you my routing number and account number. Okay. The reason I'm writing this down is because I want to point something out. They asked for the enthalpy in state 2. And I don't want you to be confused. Enthalpy is not something that we usually talk about when we're just talking about a closed system. The reason is because this doesn't really have enthalpy. Yeah, you could take its pressure times a specific volume and add that to its internal energy, but that's not really how we account for the energy in the system. The internal energy is the only energy. Okay? See, people get all tripped up with this part because they think, well, I've got an air compressor at home, it's got a tank, that tank's under pressure, so it has energy. It's kind of like a spring is some kind of potential energy, and they begin to think of pressure as potential energy and want to account for that when they see a system like this. So, well, there's pressure in there, so there must be something more than just thermal energy. But that's not the case. Remember that thermal energy, or pressure, is just a side effect of thermal energy. Okay? Pressure is just the result of the molecules bouncing around in there. Okay? That's all it is, nothing more, nothing less. Anyway, so it looks like to me we're going to have to start filling in some of this. We don't know the heat transfer, we weren't asked to find it. I don't know what all we can do over here, but let's see what else we can come up with. For example, we might be able to do something with the change in the internal energy. So let's start working on that. So let's see what properties we can get. Well, we've got the temperature in state 1, and we have the quality in state 1, right? Excuse me. So the volume in state 1 would be due to volume of liquid plus volume of vapor, right? But we could write the volume of the liquid and the volume of vapor as the mass in the liquid phase multiplied by the specific volume of the liquid plus the mass in the gas phase times the specific volume of the gas. Now, why would I do all this? Well, I already know a relationship between these two, right? It has to do with quality. And I've been given the quality. Plus, I can look up VG and VF for this temperature. And so I might be able to come up with the initial volume. Why would I care? Well, that'll help me calculate the volume in state 2. And at least I can start to work on this problem. Okay? So let's see what we can get. This term here we can get pretty easily, and this one as well. In fact, we've already said that the mass of the liquid was how much? Do you remember? 80% is from gas phase, so it's 0.04.
What?
The mass in the liquid phase?
Oh, understand it.
Remember we talked about that?
Yeah, that's what you're saying, the percentage.
Oh, I see, no. And the mass of the gas is 0.16. Okay, well, that makes sense. So we've taken care of these two. So we should be able to look up VF and VG and figure out the volume in state one. I need some more space, so I'll move over here. So help me do this. Go to the back of your book and look up the specific volume of saturated liquid at negative 30 degrees. Remember, it's for R134A. Don't go to the steam tables. Go to the 134A tables. And while you're there, we'll also slide over and get VG. So total volume 1, mass of liquid 0.4 pound mass. What's the specific volume of saturated liquid at negative 30 degrees Fahrenheit?
0.01143 cubic feet per pound mass. Yeah.
Okay.
I did the right one here. Yes.
Now, the rest of the mass is in the gas phase, and that's 0.16. Oh, keep me honest here. 0.04. There we go. So 0.16 pound mass times the specific volume of saturated vapor. Well, how much is the specific volume of saturated vapor at negative 30 degrees Fahrenheit?
4.43.
Good. 4.43 cubic feet per pound mass. So the pound mass will go away. We'll just be left with cubic feet. When you do that, you find that the volume in state one is about 0.709 cubic feet. So rather than have this mess over here, let's just write down that the total volume in state one is 0.709 cubic feet. Well, that would allow me to calculate the total volume in state two, right? All I've got to do is take the number 0.709 and multiply it by 1.4. I don't remember if I did that in my, no, I didn't use that as an intermediate step. So why don't you guys go ahead and calculate the total volume in state two. So take 1.4, multiply it by 0.709 in your calculator and see what you get. When I saw this, I went a slightly different direction. But same solution, same thing.
0.993.
0.993 cubic feet. Now, if we know the diameter of this cylinder, don't you think we could figure out what Z1 is? What is the height in state one? We could also figure out the height in state two. Why would I be interested in that? Well, if I know the difference in height, I know how much more that spring was compressed. And if I know that, then I can find out how much work was done. Now, there may be an easier way. In fact, there is an easier way. But let's approach it this way to begin with and see what we get. Okay? All right. So there's our volume in state two, there's a volume in state one. So we can relate the volume in state one to the cross-sectional area of the piston and the height. So basically, the volume in state one is Z1. Let me make it clear that there's a different height in state one than in state two. Okay. So Z1 is the height multiplied by the area, but the area is just pi d squared over 4. Okay. So if we rearrange and solve for Z1, Z1 would just be V1. And let's see, what I'll do is I'll just move this term to the other side, so I'll invert it and multiply on the other side. I said I would invert it. Let's try again. 4 over pi d squared. So then the volume in state one is 0.709 cubic feet. 4 over pi over, now d, the diameter is 12 inches. That's 1 foot, which has to be squared. So they made our math easy. So the 1 square foot will cancel with all but one of the feet there, and we'll have our height in state one of the piston in feet. So just take the 0.709 in your calculator, multiply it by 4, and divide by pi. What do you get for Z1? Good. I got 0.903 feet. I rounded it up. Okay, so there's the height in state one. What do you suppose the height is in state two? Well, think about it. V2 and V1 are calculated based on the height times the area, right? that area is the same in state 1 as in state 2. So if you went through the math, what you'd find is that the height in state 2 is just 140% of the height in state 1. So if you still have the .903 in your calculator, multiply it by 1.4 and we'll have the height in state 2. Does that make sense? Yeah, we could go through this if we wanted to and figure it out that way too, but you'll get the same thing because the area is the same in both cases. So whoever still has the .903 in their calculator, multiply it by 1.4, what do you get?
1.26 feet.
1.26. Okay? Make sure, yep, I got 1.264.
Yeah.
Thank you. All right? Now, let's play with this just a little bit more. We're trying to get at how much work goes into the spring, right? Because we're working on this basically. We started out working on this trying to get at properties. That seemed like too much thermo, so we started looking at distances instead. So let's concentrate on the spring for just a little bit. Now, the change in force on the spring is equal to K times the change in height, right? That's just the linear spring equation. Force is pressure times area, right? So couldn't we say then that area times change in pressure is equal to K times change in height? All I did is I substituted pressure times area for force. That's all I really did. Since the area doesn't change from state 1 to state 2, then it just needs the change in pressure. Okay. So now let's expand these deltas. In fact, first of all, let me rearrange and solve for the change in pressure. We're going to erase the energy balance for just a minute, or at least let's erase part of it. We'll keep this up here for later. Okay. Well, let me rearrange this and say the change in pressure is K delta Z over A. And the reason I'm doing all of this is I'm trying to relate what happens in the spring to how the system changes its pressure, because once we solve for both of these states, we'll know the pressure in both states. Okay? Or maybe we'll need this relationship in order to solve for the pressure in state 2. I don't know. We'll figure it out as we go. Okay? Now let's expand these deltas. The deltas just are a difference. So P2 minus P1 equals K over A times Z2 less Z1. Now we have Z2 and Z1, we have K, we have A, so I think we could solve for the change in pressure. In fact, the pressure in state 1 is another property that we could simply look up. We've already looked up two properties in state 1. What were those two properties? We looked up the specific volume of saturated liquid and vapor, right. So we could have just read off the pressure at the same time because it's just the saturation pressure. So at a temperature of negative 30 degrees, what is the saturation pressure, please?
9.869.
And that's kilopascals?
PSI.
Oh, thank you. I'm not prejudiced against any unit system, I'll use them all. Okay, so notice what we could do. We could solve for the pressure in state 2 from this. All right? So let's do it. So the pressure in state 2 is 9.869 kilopascals. I'm still determined to go to SI. Something's wrong with me today. Let's try PSI. K is 37 pounds force per inch. The area, this is a plus. How much area do we have? Well, we could write it in feet. I don't know if it'll be beneficial. Probably we'll go ahead and change this to feet. No, we need pounds per square inch. Yeah, so we'll change the distance to feet. So let's leave this in inches. So pi times 12 inches squared over 40. So that's pi d squared over 40. It takes care of Ka. We may as well go ahead and get the area while we're here. Why don't we just calculate? What is the area? Pi times 12 squared over 4. Did I do that? I don't remember if I
One
did that or not.
13.1,
113.1 square inches, thank you. Okay, so we can just use that. Okay, and then the height change, let's see, we could convert these into inches. Why don't you just plug the difference in your calculator? This is the only place we'll need it. So 1.264 less 0.93, and then multiply by 12, and we'll get our change in inches. I did all the conversions in one step, so. What do we have? Gonna make me do this in my head?
I got 11.27 PSI, I think, if I typed everything in right.
Well, let's get the
Oh, my
height
bad.
change first.
Oh,
You did it right, I got 11.286 PSIA.
that's not right.
Okay, so, but what about the height change?
4.284.
4.284 inches?
Yeah.
Okay, hope that's not too far off the video. Anyway, it's just the height difference in inches. And so then, you guys agree with me then? 286 PSIA?
Yeah.
Now, how do I know that's the absolute pressure? I wrote PSIA, not PSIG. Don't we have an atmosphere? How do I know it's PSIA?
It's open above that, isn't it? It's open.
It is open above it, but what we have to understand is that this pressure we're talking about here is an absolute pressure. That's the pressure in state 1. All that this piece does is change the pressure due to the spring. So when the spring is compressed, that just increases the pressure. So this is a delta P. This is the PSIA part, and so it remains PSIA. Does that make sense? So there's the absolute pressure. This is very important. The absolute pressure in state 2 is 11.286 PSIA. Why is it important? Because now we have two properties for the second state. We have a volume and we have a pressure. Now, if you go back and you look in the saturated tables for R134A, you won't find volume in there, right? You'll find specific volume. So what should we do at this point? Well, there's two things that make this class harder than 220. One of them is that we pull little tricks like this with a spring. You may not think to play around with that until you come up with a second pressure. The other trick is that frequently we'll use volume to find a property. Let me show you what I'm talking about here. You know the volume in state 2. You also know the mass in state 2. It's the same as it was in state 1. So you can find the specific volume in state 2 just as its property. Okay, so I'll show you how to use this. Specific volume in state 2 would be the total volume in state 2 divided by the mass. Total volume is 0.993 cubic feet. The total mass is 0.2 pound mass. Okay, so plug that in your calculator. What do you get for the specific volume in state 2? I would have done this somewhere here. Good. 4.965 cubic feet per pound mass. I rounded it off to 4.97, but that's fine. So now we have the specific volume in state 2. We got it from here. Oh, why the heck would we care? I'll show you. Go to the saturated tables, but go to the pressure tables. And look for a pressure of 11.286 PSIA. Guess what? It's not there. Right? What pressures are there? What's that? 11.306 is there? Because you're in the temperature table, right? Okay. So you see 11.306 PSA, is that correct? Okay. What about the specific volume? What do you see for specific volume? Just assuming this is close enough. What's the specific volume of saturated liquid?
At that pressure?
Yeah, it's that pressure.
0.0115.
This is a whole lot more than that.
Yeah.
So it takes up a whole lot more space. So what is it, a gas or a liquid? I mean, most of it's gas, right? So what's VG at that pressure?
3.8988.
3.8988. Well, wait a second. The pressure is a little bit lower, yet the specific volume is a little higher than the data point in the book. What does that mean? Mean that it's mixed? I'm trying to think. I'm not sure that it means it's a mix. Let's find out. Let's interpolate. I think that it means that it's superheated. But we'll have to decide and think about it. Because if the pressure is a little bit lower than the data point in the book and the specific volume is a little higher, I think both of those lend to it being superheated. But I'm not sure. Let me show you what we have to do now. This stuff is pretty much done. Why? Because we've solved for what we needed, right? And I've even forgotten what we were supposed to find. That happens a lot of times in these problems. You start playing with them and you forget where were we going. We're supposed to find the enthalpy in state 2. I remember now. But notice that we've managed to solve for state 2 without using the energy balance. This is not common, okay? I try to point out problems that we can solve, and I like this problem because it has some good elements, but most of the time you'll end up having to use an energy balance. In just a minute, we might play with this a little bit more, okay, and see if we can do anything more with it. Okay? But for right now, let's go for what they asked us to find. So what we'll have to do is interpolate in the table. Now, instead of, I think the number that was given in the table you guys were looking at was back at the temperature table. So we had that odd pressure of 11.3 something. Go to the pressure table, which is just should be one page forward. And let's see if we can get rid of that for now. And what pressures do we have around this pressure?
Yeah, 10 is really about it.
10, and what's on the other side of it? 15, okay. How about the specific volume of saturated vapor?
4.375.
For the 10, it's 4.375?
Oh, there's a 3 at the end of it.
I'm sorry?
There's a 3 at the end of it.
A 3 at the end of this. Thank you. How about for 15 psi?
2.988.
Okay. 2.988, I thought it was, oh, we were looking at another table. Okay. So as the pressure goes up, the specific volume of saturated vapor goes down. Now we're at a pressure in between here, and yet our specific volume is higher than even if the pressure were reduced, right? So that indicates we are definitely superheated, okay? So now we should move away from the saturated tables and go to the superheated tables. All right, now unfortunately the superheated tables don't have a pressure of 11.286 either. This is a place where ease comes in very handy, okay? And I don't push ease in 220, I don't make you use it. But ease is engineering equation solver. And it's a pretty good solver. You can give it a system of equations and it'll solve them for you if you've given it the right number of constraints and everything. You can iterate it and do all sorts of things. But what I really like about ease for thermodynamics is it has a bunch of property data tables built into it. Okay, so it's really nice that it has that. Now I have you do some work with ease because I want you to get used to using it. I think it's very valuable. Anyway. So now go into the superheated tables. What pressures do you see for superheated R134A that are close to 11.286? Is it 10 and 15 again?
Yeah.
Okay, so that would be two separate sections of the table, right? Okay, so we're going to have 10, 15, and there should be a specific volume in that. Now, you have to have another parameter, right? And so the other parameter we have is the specific volume. Okay. So what specific volumes do they have at 10 and 15 that are around this specific volume? Well, at 10 there's one set, and at 15 there's another, right? Mm-hmm. So we'll have to interpolate. Now, for the sake of the video, I'm probably going to cut the video off because I've got to go over to the computer and work in Excel to do this because it's easier to understand. So if you're watching the video, download the spreadsheet that I'll put next to this video and you can look and see how we finish this off. At this point, it's basically an interpolation problem. Okay? Another way to solve this is to take these two parameters and use E's, engineering equation solver, to get H2 and T2. That's the easy way to do it. So it's called E's. Bad pun, but we're engineers after all, not comedians. Okay? So I'm going to go to a spreadsheet. We're going to figure out how to interpolate and find the enthalpy and temperature. But before we do that, for the sake of the video, let's look at one more thing. Remember I was talking about the energy balance. In some problems, what you can do is you can rearrange it. And I don't know if you remember this trick, we'll come across it again, but basically you could combine the boundary work with the internal energy change and come up with an enthalpy change. And you might be tempted to try and do that in this problem. The only issue is that the only way you can do this is when the pressure, is constant. Do we have a constant pressure process here? We don't. And so in my opinion, their question about enthalpy is inappropriate. They should have asked for internal energy. Because enthalpy is not really relevant. It doesn't help you in this kind of situation. The system does not contain enthalpy. It contains internal energy. So there's no way of combining the boundary work with the internal energy to get anything like enthalpy that would have any relevance. Okay? Anyway. Okay, so I'll stop the video and we will go to the computer.